Well, good afternoon, everyone, and good evening to those of you on the other side of the Atlantic. This is Craig Maddox with Moberg Analytics, and it's a special edition this week because I'm actually in Philadelphia here with our founder and CEO, Dick Moberg, and our VP of Product Development and Research, Ethan Moyer. So it's been a cool week. I've been here. And so let's get started. As you know, our mission at Moberg is to help build tools and assist in the mission of treating brain injury, and it's to help you. And these webinars are an extension of that mission. We do tutorials with case studies. We have amazing guests come on and present their work linking AI with treatment and research of neurocritical care. We're also establishing some starter grants of in-kind cloud time tools and consulting to help if you have your own project and want to get started, get it off the ground, you need help in that area, we would love to speak with you. As always, please give us feedback using the QR code or the link here on our website, or you can email me directly at that email address. Also, a reminder, we've building up a nice little library of these sessions now, so don't forget to go back and pick ones up that you might have missed. We've got 9 out there there's a link on our website that you can reach them all. So some amazing, fascinating topics and amazing people, and so it's been really cool. Also, some of the webinars, we include assets like Python notebooks and data sets that you can have a look and run the algorithms yourself. If you have any questions about that, you can email me directly. If you have questions, please use the Q&A feature of the Zoom chat. Everyone's well familiar with that now. And today we are very excited to welcome 2 people that we met through Airtopakuri at the Brain Physics Lab in Cambridge. First is Agnieszka Kazimierska. She's an assistant professor at Biomedical Engineering Department at Wroclaw University of Science and Technology in Poland. She's a member of their neuroengineering BrainLab. Her research focuses on biomedical signals related to blood flow and pressure in patients with intracranial pathologies. And she develops methods to analyze ICP and arterial blood pressure waveforms. Today, she's got a fascinating talk. She's going to talk about an automated pipeline for classifying ICP pulse waveform shapes and deriving something called the pulse shape index, and how she's incorporated that. This is the cool part too, how she's incorporated that into real-time continuous monitoring. So our whole purpose and our whole goal in life is to be able to bring these amazing new technologies back to the bedside to help patients. We're also joined by Cyprian Mataczyński. He's finishing his PhD also in the Department of Computer Engineering and BrainLab in Wroclaw. His research focuses on medical applications of neural networks, and he does projects related to intracranial pressure monitoring in areas like waveform morphology, forecasting ICP crises, and artifact detection. And today, he's going to discuss his work predicting ICP crises using a TabNet predictive model and show us how the feature important masks can help explain the crisis episodes. So with that, I will be quiet, stop sharing, and turn it over to our fantastic guests. Thank you guys so much for being here today.
Thank you so much. So allow me just a moment. I will share my screen now because I will start. Yeah, you should be able to see my screen now.
Yep, we can see it. Thank you.
Thank you. So thank you very much for the introduction. So my name is Agnieszka, and together with Cyprian, we'd like to present our work on incorporating deep learning in the analysis of intracranial pressure, particularly in traumatic brain injury patients. And I will start with the first part, which is ICP pulse waveform morphology assessment. So what is the motivation for our work? So it is well known that the relationship between pressure and volume in the intracranial space is strongly nonlinear, and that pretty much ICP alone, the mean ICP alone, is not enough to tell us if the patient is actually at risk of intracranial hypertension. So we could have patients who are in the so-called good compensatory reserve stage, where the changes in intracranial volume produce very little changes in pressure. But we can also have patients who are at the steeply rising part, the exponentially rising part, where a given volume increment may produce a small change in pressure or a very, very large, very disproportionately large change in pressure. So what we would like to do to monitor those patients and to determine if a patient is at risk of intracranial hypertension would be to determine where they are on the pressure volume curve. And cerebrospinal compliance is a parameter that describes how large of a change in pressure we can expect for a given volume increment. So patients who have good compensatory reserve, they have good compliance, high compliance. We can assume that they are not at a high risk of hypertension, but as compliance is reduced, as we move towards the steeply rising part, compliance could tell us that the patient is actually at risk. But the problem with assessing compliance directly is that to determine the absolute value, we would need to know the volume change that produces a given change in pressure. And in TBI patients, it would be very dangerous to introduce changes to the intracranial space that could produce, for example, uncontrolled hypertension. So for a long time, the researchers have been looking for a way to determine whether the patient is in the good or bad compliance conditions, so to speak. And it has been determined that at least some of the information on the cerebrospinal compensatory reserve is contained in what we call the ICP pulse waveform. So the ICP pulse waveform, we can define it as the changes in ICP over a single cardiac cycle. This is marked here in the red part, and they are related to the arterial inflow and then venous outflow of cerebral blood over a single cardiac cycle. And under normal conditions, those oscillations have a very specific shape with three characteristic peaks, the P1, P2, and P3, arranged in a, let's say, a triphasic sawtooth shape with P1 as the dominant peak. But it was also observed that as compliance decreases, as the pressure volume compensation starts to change, the shape of the waveform also changes. So we start with the normal waveform, the triphasic waveform, but as compliance is reduced, we observe increases in the P2 and P3 peaks that start to overtake P1, and eventually the waveform starts to resemble a sinusoid or a triangle. The peaks are no longer clearly visible. And our approach, our idea was to use deep learning to produce a metric of the overall waveform shape. Rather than determining individual peaks, detecting individual peaks, which is very difficult in the ICP signal, we wanted to provide a summary metric of what the waveform looks like. And the approach that we propose, the end-to-end pipeline, as we call it, is a way of doing exactly that. So we start with a full intracranial pressure recording. It could be, for example, several days long. It just needs to be a high-resolution recording for the waveform to be visible. The first step of the algorithm is to detect the individual pulses. You can see the pulse onset markers, for example, here, and then process the pulses before they are passed to a model. So the processing that we do here is twofold. First, each of those individual waveforms is resampled to a uniform length, because we want to remove the effect that changes in heart rate have on the duration of the waveform. And the second processing part is to normalize the waveform, because we also want to remove the effect of the pulse amplitude on our results. So the idea of our approach is to focus solely on the waveform shape, removing the changes in pulse duration and amplitude. And each of those pulses is then passed to a residual neural network model that we trained. And I will go back to details on that in a moment. And this network produces a classification result on a scale from 1 to 5. So we determined 5 classes that should be found here. So 4 of those are valid classes, or we call them valid classes. from 1 to 4, which represent the changes in the waveform shape, specifically the changes in the relative height of the peaks and the visibility of the peaks when it comes to the pathological class. So we have class 1, which we consider normal shape, the normal waveform shape, moving through possibly pathological, likely pathological, up to the rounded or triangular pathological shapes. But in addition to the 4 valid classes, we also determine if a pulse is an artifact or not. So we call it the so-called artifact class, because rather than adding an additional artifact detection and removal step, we chose to find artifacts at the same time as we process the individual waveforms. And the model that we trained, the residual neural network, was trained on data from TBI patients from Wroclaw University Hospital that we collaborate. It's a hospital in Poland. And we used long-term ICP recordings to produce a training validation set and as well as an additional testing set. So the training validation set was approximately 21,000 pulses that were randomly selected from those long-term recordings, and then they were manually annotated into one of those 5 classes that I mentioned earlier. And to test the generalization ability of our model, we also used a testing set. In this case, 650 pulses from a completely independent cohort that consisted of aneurysmal subarachnoid hemorrhage patients. And those pulses were annotated by a panel of 3 experts to provide an independent, well-annotated cohort to see how our model fares in data that it hasn't seen. And we tested different kinds of models, different architectures, different input types, but eventually we arrived at the model that worked best or provided the best classification accuracy. And this was the residual neural network that you can see later in code how it's structured. That takes as input one-dimensional vectors of ICP signal samples, so very limited preprocessing is required here, only that those signals are normalized and resampled. And here's an overview of the model in terms of its accuracy. So we achieved the accuracy of 93% in the validation set and 82% in the independent testing set. And when you look at the confusion matrices that are shown here, we also observed that the model very rarely mistakes normal pulses for pathological or vice versa, but it does make some mistakes when it comes to adjacent classes, so 3 to 4, 2 to 3. This is mostly because the classification that we proposed is discrete. We only have 4 classes there, whereas the changes in ICP are more continuous. So it's a way of approximating all the waveform shapes. But as mentioned, we wanted to look to a solution that would allow us to process it in real time. So we also tested how the model fares when it comes to processing time and the computation burden that we have. And we tested that the model is actually capable of processing in near real time. I say near real time because we need longer chunks of the signal. In this case, we tested on 10 seconds because we need a longer part of the signal to actually find the individual pulses, but the processing time for a given 10-second chunk is much, much lower than the collection time. So we could potentially add it to a real-time monitoring scenario. But what we also observed while working on the classification was that tracking over time for different classes or the percentage of pulses assigned to a class is not ideal. It's especially in the ICU setting, which is already overburdened by information. So we wanted to propose a summary metric, something that would be easier to track over time. And that's how we arrived at the pulse shape index that was mentioned in the introduction, or PSI or PSI, depending on how we read the abbreviation. And the pulse shape index is exactly a way of finding a summary metric for the classification. So we start with the classification that's produced by the model. We have the 4 valid classes, We remove the artifacts at this point to exclude them from the results. We want to clean up the signal a bit at this point. And what we get is the full class time course. So each of those schematically presented here dots each of that is an individual waveform. And from that, we calculate a weighted average, a moving weighted average. So we take 5-minute moving windows that are shifted every 10 seconds. And for each of those windows, we calculate the weighted average of the class numbers, I, so from 1 to 4, and the percentages of pulses assigned to given class, which are the weights here. So, and this gives us an idea which pulse type is actually dominating or which pulse types are present in a given window. And you can again see here schematically how it looks like when we move from this discrete classification for individual waveforms to a continuous metric that can be tracked over time. So the more pulses of a given class, this value would be dominant here. And the overall interpretation of the proposed index is as follows. A value close to 1 means that we only or mostly see normal waveforms, the three-phasic sort of like waveforms, which suggests that the compensatory reserve is good. And values close to 4, so the other end of the scale, mean that we mostly see pathological waveforms, rounded waveforms, and this suggests that the compensatory reserve is actually exhausted. And you can see how it schematically relates to the pressure volume curve. And here's an example of what it looks like when we process an actual ICP recording. So we have a mean ICP trace here, the pulse amplitude of ICP, and the individual pulse classifications in red, with the PSI trace overlaid in black. And this is an interesting example because we can see that the PSI changes occur actually earlier than the increase in ICP that we see at the end of the recording here. So in some cases, we can see that the pulse morphology actually changes before mean ICP does, for example, in this case. And so far, in terms of clinical interpretation of the index, we've done 2 major studies on the PSI, both in the Center TBI High Resolution database. So the first study was the relationship between the pulse shape and outcome after TBI. And the second study, the relationship between the pulse shape and CT features of TBI patients, especially in this case, midline shift and mass lesions. And when it comes to the relationship with outcome, we observed most of all that elevated pulse shape index, so pathologically altered waveform shape, actually correlates with mortality after TBI. You can see it, for example, here that patients who died had elevated PSI compared to those who survived. But the most interesting part was the relationship between mortality or poor outcome PSI and mean ICP, because looking at the data, we also saw that in patients with poor outcome, the changes in PSI were already statistically significant even if ICP was relatively low. So when we divided those patients into those with ICP below 15 millimeters mercury and those above 15 millimeters mercury, the changes were not as pronounced, but at relatively low ICP, the difference in PSI was much larger. And you can also see it in this plot up here, which shows the relationship between the pulse amplitude and mean ICP, as well as PSI and mean ICP. So we observed here that while patients who died showed in general higher pulse amplitude than those who survived, the trends in both groups were more or less similar. So in both cases, the pulse amplitude increased with increasing mean ICP. But when it comes to PSI, patients who survived actually showed a pronounced increase in PSI. You can see here, well, mostly in this part, which is in line with what we expect on the basis of the pressure volume curve, that the pulse shape will change ICP, but very interestingly, in patients who died, the pulse shape was already pathologically altered, even if ICP was relatively low. And again, when we looked at the CT features, specifically, we looked at the presence or absence of midline shift and mass lesions. We saw that PSI was elevated in patients with midline shift and with mass lesions present. And compared to mean ICP and the pulse amplitude of ICP, it was the only parameter that statistically significantly differentiated those two groups of patients, which suggested that PSI is a better indicator of the presence of pathological features than the other two, and it shows us or reflects the volume imbalance in the intracranial space to a larger degree. And when we looked at the classification, binary classification, so whether the first 24 hours of monitoring from which we derived the pulse shape index allowed us to classify the patient as presenting or not presenting the pathological CT features. We also saw that PSI has a much higher AUC compared to both mean ICP and the pulse amplitude. And altogether, those results suggest that in TBI patients, we see disturbances in the pressure volume compensation, which are reflected in the waveform shape, and the volume imbalance is mostly reflected in this case in the waveform shape. And those are the clinical results, the major clinical results we have so far. And also, as mentioned in the introduction, to enable the use of our solution, to promote the use of our solution in real-time monitoring scenarios, together with the ICM Plus team, we developed a ICM Plus plugin, an ICM Plus Python plugin that uses the model that we developed to calculate PSI. This is, you can see here, it's available at the function list, and this is an overview of the code that we use. And here's an example of what it looks like if we actually process PSI in ICM Plus. You can find the source codes, the ready-to-use source codes for the plugin in our GitHub repo. But to give you a better idea of what the code actually does and how it's structured, what are the components of this plugin, I will now pass the mic over to Cyprian, who will show you the source codes in the repo, as well as a notebook that shows you how to use it, what are the use cases. So Cyprian, over to you now.
Thank you very much. And let me share my screen. Okay, so you should be able to see the notebook. So as Agnieszka mentioned, our code is openly available along with the network weights and can be downloaded from our GitHub repository, which is under this link, or if you scan the QR code here, you will get the same result. And there you will find basically the repository for the ICM plugin, but also within that, you will have a pulse detection library that we developed for just the to use from just the Python level. So let's go over how does this thing work. So first of all, because we are using, or rather we are deploying neural networks, we want to make use of a hardware that we have available. And because of that, we encourage you to install the environment straight from the files that we provide. So first of all, we provide the Anaconda environment that will install the version of Python that the model was trained on, along with some of the requirements, but also because of the hardware requirements, if you have CUDA 11.7 compatible GPU, then you would need to install one of the two different types of requirements for the GPU to be available for the code execution. And so those are requirements GPU and CPU for those that do not have the GPU available. Both of those should run pretty fast, but of course the GPU will run a little bit faster. And now for what you can find within that repository. The main code for our plugin consists of 4 files. First of all, just the neural network model definition, which is the ResNet model pi found in model, along with the weights that it has after the training. And it is used within the pulse classifier part of the code, which extends the classifier class that basically takes care of the whole classification process. So first of all, it pre-processes the pulses into constant length, then it batches the data so that it will be much faster than passing one pulse after another, and then it classifies it using the ResNet and gives us the pulse classification result. But we have also here the segmenter class in the pulse detector .py, which segments the whole signal in whole ICP signal into single pulse waveforms by first filtering and linear trending the parts of the signal, but then it uses modified Shulman algorithm to produce a detection result for the whole pipeline to use. And both of these parts are connected within the classifier pipeline, which basically tries to streamline the usage of the library through a single callout to the function that does everything for us. So we just provide it with the ICP signal and the time vector, and having that, it estimates the sampling frequency, and then it does all the computations I've mentioned while returning the results. So looking at it from the code level, we can see that within the classifier pipeline, we have the processing pipeline class extended with the process signal method that is the main method that takes signal and time arrays and returns for us the classes and times after classifying and passing the whole signal through through our process. While in the pulse detector, we have the segmenter class that has the split pulses method that again uses the signal and time, while also needing the an additional flag of a mean time and estimation of the sampling frequency, and produces for us both pulses. So that will be the list of the values for each pulses, for samples belonging to each pulse, times, which will be either a mean time, a single mean time for each pulse, or a joint vector that corresponds to each of the samples of the pulses, and peaks, or rather onsets of the waveforms that can be traced back to the ICP signal as an ID. And finally, the classifier part, which basically extends a single method of classify batch, which takes lists of pulses and produces a list of predictions. So how would you use our project? So because if it is distributed as a GitHub repository, we encourage you to just download it into some part of your environment, and then once you have that place, you can use it by adding the directory it's in into the Python path Python path environmental variable. And once we have that, and to be exact, we need to pass the pulse detection place, then we can import straight from the files both the processing pipeline for the whole process and single processes like segmentation and classification separately. And let's now go over an example. So I've run this code a little bit earlier just to save us a little bit of plotting time. For this code, we will be using one of our files, which basically contains just two vectors. One vector is a time vector, and the second one is the intracranial pressure vector in the millimeters of mercury. And what we can see is that it has more than 4 million rows. So we will cut this down into a 6-hour window. And we can plot this to check out how does the signal look. And if we zoom in a little bit, we can see that it indeed has pretty good quality, in which we can recognize each of the shapes separately. So we can use that. We can use this file in our processing. And to do that, we first need to make sure of two things. First of all, we need to check for any not numbers, so any missing data from the signal. Because of current implementation of the modified Shulman algorithm, which is vectorized and thus it can't take any non-values. And for the second part is that we need to make sure that the time vector is in seconds. For us, it is, so this is not a problem, but the usage of our pipeline is extremely simple. With that import, we just create an object of the class of processing pipeline, and then the whole pipeline can be called with just a single call that we pass the raw signal and the time. And as a return from that class, we will get a vector of a list of vectors of 5 numbers. And each of those 5 numbers is a raw output of the network. So before the softmax application. And because the softmax is monotonous, then just choosing the highest of those numbers will give us the ID of the class that the network has predicted as the most probable here. So just the NumPy argmax function will suffice for that to be translated. And because this is an ID, and Python indexes from 0, then our classes will be shifted by 1. So class 1 will have the number 0 and so on. And if we look at the detections here, you can see that this recording was pretty diverse, having each and every class and having even a little bit of artifacts. So let's look how does it look on the signal part. So let's zoom in into some part of the signal again to look at the exact predictions. So for example, around here, we can see that under the midpoint, around the midpoint of each of the waveforms, we see correlating class with mainly the first class being predicted all the way here. And if we now recall the PSI index definition, then we can compute it here very, very easily. So first of all, we filter the artifacts. So that would be the class number 5 or the ID number 4. And then we will compute the psi in the 5-minute window with step of 10 seconds, one after the other. And once we do the rolling window here, we just choose based on the time vector the part that we will be analyzing, and then compute the percentages of each class within that part. And once we have that percentage, we multiply it by the class number and add it to our result. And this is extremely simple process that allows us to create a graph of psi for this signal. And you can see here what Agnieszka has mentioned previously, that even though the ICP stays at around 10, 9, 10 to 12, we see a gradual psi rise just before an event where it rises much more along with the psi. So this is the psi computation, and if you would like to go a little bit further, you can use the tools that we provide separately. So both the segmenter class and the classifier class, you could use them separately for any needs that you would like. For this example, we will show you how you could check whether the signal has pretty good quality, or rather waveform quality, and how to check the average of each predicted pulses. So for that, we will use the classes separately. So for a segmenter, we've imported it in the beginning. We just need a sampling frequency, which here we estimate to save time, so just the first 2 times. And we assume that the sampling frequency is constant across the whole signal. And once we have that, we can use segmenter split pulses method with the signal, time vector, and the estimation to detect the pulses. So again, we have just a single line for that. And if we plot this, we can again zoom in into some part of our signal to see how well the algorithm did. And we can see that the detected peaks or detected onsets of the waveforms are exactly where they supposed to be, at least in this part of the signal. So next part would be using the classifier. And for that, we need to specify a little bit of parameters that are basically a hardware parameter. So where are the weights located? What is the batch size which will be used? So this will determine how much memory, RAM, or VRAM for the GPU it will use, whether we want to use the GPU, and so on. And to use the classifier, once we have those parameters specified, it's again a single line of code that passes the pulses argument that we got from the split pulses here. And once we have that, we can use the predictions to divide all of those pulses that we saw and create a graph of mean pulse waveform with Q1 and Q3 as an area plot over the waveform. This is a pretty simple way of showing what Agnieszka has mentioned previously. So we see that in the first class, the first peak is very pronounced, very high. And then in the second class, we get much higher peaks of second and third peak, and in the third class the first peak starts to go down, while the fourth class is here it's almost a sinus-like graph. But we've omitted the artifact part, so now we can check the signal for any artifacts, and we can see how it did. And on the waveform level, we can see that indeed some of those very rapidly spiking parts of the signal are pretty easily detected by the model and annotated as a part of an artifact. And if we wanted to, we could remove them for example, from further computations altogether. So this is a really simple way of using what we have on the repository. And now I will come back to the prediction of ICP crisis. So because we have seen that the PSI might let us a little bit, give us a little bit more information on the on how dangerous the patient's state might be. We went on to trying to define what we call an ICP crisis. So we started off from a definition of intracranial hypertension, which we had set here as a threshold of 20 millimeters of mercury for at least 5 minutes. And those episodes, those intracranial hypertension episodes, then were filtered through 3 different thresholds. So first of all, we measured pressure time dose of each of the episodes. So basically measuring the intensity, because pressure time dose is the area over the threshold and below the ICP signal on a given scale for the whole episode. Then the pressure reactivity index, so whether the cerebral autoregulation is impaired, and pulse shape index, which more or less translates into the compensatory reserve information for our crisis. And the thresholds that were chosen here were chosen because of within the data, we have seen that those thresholds, the episodes with those thresholds almost never happen in patients that have survived. If I recall correctly, only 2% of patients who survived had such ICP crisis, but almost half of the patients that died did have one or more of ICP crisis in the recordings. And so, because those ICP crises are pretty rare, we needed a large database to try to even try to predict them. And in collaboration with the people from Cambridge, we collected almost more than 1,000 patient database. So both the Center TBI databases and Addenbrooke's hospital databases were joined. And then after some exclusions, we were left with more than 700 patients with over 6,000 days worth of signal, of different signals, not only the ICP signal, on which we did the retrospective analysis to annotate the signal for any intracranial hypertension, and each of the intracranial hypertension were assigned the values of PTD, mean PRX, and mean PSI to have the data ready for ICP crisis prediction. And our approach, because of the amount of data and the computational limitations, we decided to tabularize the data, but tabularize it in such a way that we will be able to later on explain a little bit more on what the model looks for in those signals. So what we did is for each data point, which have chosen some time within the recording, and that time was always a finish time for a window that would be that would tell us about the scale of the process happening. So from 4 hours to 30 seconds long windows. So the shorter and shorter windows would end at the same place, and we would window different signals, so from intracranial pressure and arterial blood pressure raw signals, and the derived signals like pulse amplitude of ICP, pulse shape index, pressure reactivity index, and heart rate. And each of those we would compute basically some way of knowing whether we are looking at the mean, so this is just mean, or at the dynamics of the signal changes, so either amplitude, standard deviation, or any of those given here. This gave us 252 features, and additionally we included patient's age as a metadata feature for each of those recordings, to a total of 253 features. And we wanted to create something that will tell us exactly what does it use in its prediction. What is the main predictor for the ICP crisis, or anything other that it predicts. And because of the very simple additive features of the tabnet masks within the tabnet masks, we could create a model committee that would consist of a few tabnets that would reduce our number of false positives, but it would also allow us to explain the whole process pretty easily by just summing the masks, because each of the models were predicting a little bit different thing. So the first model was predicting whether the intracranial hypertension will happen. Then three other models were predicting whether that intracranial hypertension will have met at least one of the thresholds, so either the PTD threshold, PRX, or PSI threshold. And the final model was trying to predict the whole ICP crisis, so intracranial hypertension plus all three of the thresholds met. And once and only when all of the models were in agreement, we could aggregate those into a single positive ICP crisis prediction. And the results are here. We get very high accuracy and recall because of the imbalance in the set, while we lack on the precision when it comes to some false positive data. We miss almost never the ICP crisis happening, but we still have some false positives that might or might not be bad false positives, but I will come back to that a little bit later. So because I've mentioned that one of our models, just a part of the committee, predicts the intracranial hypertension, we could try to compare ourselves with other state-of-the-art performance models that try to do the same thing. Because the intracranial hypertension definition is different across those models, so from 30 in Giza, and then around 20 in Petrov, Husser, and Myers. If we compare ourselves in our group, we get the same or better scores, but not falling that short of Giza at all, of 30 millimeters mercury prediction. And finally, what's the most interesting is we can look a little bit deeper into the formation of such crises, the main predictors that we could see, and we can look at it both globally. So on the left we have a global ranking, and locally on each of the predictions being made in real time. We can generate, or rather we don't need to generate anything, because it will be the mask within the tabnet will be generated during the prediction. So we just need to extract it and then check for the values that it produced. And what we've seen here is that the main drivers, the main three drivers for the prediction of the tabnet model are pulse amplitude, ICP, and PSI. But because of the windowing process and of the tabularization, we can also look at which of the parameters are the most important for each of the signals. So for ICP, we see a very high mean information, while in both PSI and pulse amplitude, the main predictors are the changes within those signals. So dynamics of those signals, either amplitude, standard deviation, even amplitude of the derivative of the signals are the main driving points in those two signals. So we don't look as much as on the mean of those, but much more on the changes that are happening through time. And if we look at second by second prediction, we can see this is some example where we had an initial bad prediction, probably due to recent rises in ICP, but later on the models weren't sure whether the ICP crisis is coming. To be exact, the ICP crisis, annotated ICP crisis, is the red part of the signal. So here is the place where it starts, and the yellow part of the signal is the place where all of the models are agreeing that in half an hour there will be an ICP crisis happening. And for this part, the main driver that ICP crisis is not happening is the amplitude of ICP. So this signal was the main driver. And once we were getting closer and closer to the crisis happening, we saw an increase in the ICP in just the ICP importances, while the amplitude importance decreased a little bit over time. And because of such detailed information, we can generate for each of the seconds what we would need to look at to see what might drive a future changes within the patients. And that is something that we would need to look into a little bit more. And so if you are interested in our research, here are some of our works. You can find more information on what we've shown here there. And thank you very much for listening. If you have any questions, please don't fear to ask. Thank you very much.
Wow, thank you both very much. That was amazing. If anyone has questions, feel free to enter them into the Q&A, or if you want to come off mute, raise your hand and we can bring off mute. That was so cool. The explainability of it, and when you showed the chart of how much in advance the PSI started to change, wow, it seems like it has a lot of promise to be an important index in giving an early warning for these crises. This is amazing work. And I guess I don't have a question. We're all sitting around the table here, just kind of open-mouthed and amazed, speechless. Yeah, that's the word, at this. So anyway, this is really great work.
Thank you so much. I think we have a question from Marek, but I'm not sure, because the question is what is better, but I'm not sure among which parameters. Oh, that's the PSI or PRX. I wouldn't say either is better, because they are obviously interconnected because it's the same system, but they are, or at least are believed to, represent different things. And Cyprian showed some examples of the explainability analysis here, but in some cases we see that PRX is very important in terms of the prediction. In other cases, the compensatory reserve-related parameters seem to be driving the prediction. So I think what we actually need to do is look at them both, hence the ICP crisis definition that we try to incorporate both the cerebrovascular reactivity indices and the compensatory indices. I think what we actually need to look is all of them.
So where are you taking this? What's next for the research, or are you looking at more clinical implementation now? What's on the horizon for the two of you with this work? Because it is amazing.
I think what we definitely would like to do is to explore the pulse shape of ICP and its clinical applications some more, perhaps some other scenarios, because we focus mostly on TBI in this particular project, but it's not the only scenario where ICP is measured. So we're hoping to extend it to other patient cohorts to see what we actually can do. We are also looking at other signals, because the PSI or the classification approach is just, in general, it's a way of looking at the signal, of trying to derive a metric from the signal. And we would like to do that for other signals as well. I personally am looking at arterial blood pressure mostly, but we hope to extend it to see where it takes us with other signals, perhaps to create a larger pipeline to analyze different signals simultaneously. And I think mostly we would like to see what else we can see clinically, because one of the most important results, or the ones that they were not exactly surprising, but we were actually very fascinated by it, was the relationship with the CT results, and how we can see what is happening in the imaging, in the signals, the changes in the signals. So hopefully we can extend it to other metrics. There's the TBI is such a complex clinical entity, let's say, that there are so many parameters we can still look at that it's hard to decide one particular direction. To be honest, we'd like to look at everything.
Yeah, cool.
And as to answer Marek's questions, I think I don't know if we can combine PSI and PRX into one index, but we would definitely like to move forward with the combined analysis in terms of analyzing those jointly to see, because I think this is one of the major messages we have in the ICP crisis prediction, is that it's not just one parameter. We need to look at a lot of things simultaneously, because it's such a complex state, the traumatic brain injury.
Yeah. Cool. Well, if there are no more questions, we will wrap up with, again, our gigantic thank you for coming on, and thanks Erika for introducing us to this amazing team. This is really cool. The recording will be available on our website within a day or two, and thank you again so much and have a great evening.
Thank you so much for having us, and to Erika again for introducing us.
Thank you very much.
Thank you.
Take care.
Thank you. Take care.
Take care.